Hello and welcome to Mechanical March for Exercism. I will start the actual material in 1 minute. It looks like Twitch is running, which is good. If you're listening in the stream, I will have the comments from the stream on my screen. All right. I will be implementing I will be solving some of the exercism exercises for 12 and 23. Mechanical March, we're featuring languages like C, C++, and Go. So I will be solving a handful of exercises in Go. My plan is to solve 3 exercises in particular. I'm going to be solving the pangram exercise. Then I will solve the parallel letter frequency, which is not one of the suggested exercises, but was suggested as a good way to demonstrate how to do parallelism in Go, or concurrency rather. And then thirdly, I will be looking at the binary search. Hello, people in the chat. All right, so my setup here is, I hope my font is big enough. I tend to use Terminal for everything. In my top left pane, I have my editor, Vim. In my top right, I have, every time I save the file, I will see the test results, the Go test, and then I have at the bottom the Twitch stream. So the first exercise here is the pangram exercise. Given an input string, we need to determine whether or not it's a pangram. A pangram is defined as a string that has every letter in the alphabet. For example, the quick brown fox jumped over the lazy dog. It has A, B, C, etc., all the way on through Z. There's a lot of different ways that people tend to approach the exercise. The 2 most common approaches you'll see is people will iterate through the string and they will track which letters were found. So, you go through the quick brown fox jumped over the lazy dog, you start with the word the, T, H, E, you say a T is found, a H is found, a E is found, you get to the end, you check that all the letters are found. That's a pretty good way to solve it, but not necessarily the most efficient. Usually the way you explain how to solve this, if you were giving someone like a sentence written on a piece of paper, you say, how do you check if it's a pangram? Well, you check if A is there, you check if B is there, you check if C is there. So that's the approach I'd like to take for this exercise. I'm going to iterate through the alphabet from A through Z and check that each letter is contained within the string. If all the letters are contained, we have a pangram. If not, we don't. So I don't like panic. So the first thing I usually do is I'll just put in a return false, just to make sure I'm returning the right types. If I save this, we'll see in the right pane, it will tell me all my tests are wrong. For example, the first test, it says perfect lowercase ABC is false, want true. So we need to actually implement something here. So again, what I'm going to do is I'm going to iterate through the alphabet from A through is less than C. This will give me a loop that will iterate through the alphabet from A to Z, and I can check that every letter is present. If all the letters are present, we have a pangram. If one of the letters is not present, we don't. If do some pseudocode here. If letter not present, return false. And then if we manage to make it through the loop to the end and all the letters and none of the letters return false, then we do have a pangram, so we return true. So all we need to do here is check if the letter is present, and the way we do that is by using the strings module, strings library. The string library has a contains rune that lets us take the input string and the letter, and it will tell us whether or not that's not what I meant to do. This will tell us whether or not the rune is in the string. So what we actually want to do is put it here. if not contains rune, return false. So if the string does not, the input does not contain one of the letters, then false is not a pangram. Otherwise, we get to the end and is a pangram. That should more or less work. Should that be strings? And define strings that contains rune. Golang string. Forgot to close some of this stuff before I started. Contains, oh, it should be an uppercase. Contains, yeah, we need an uppercase contains rune. There we go. So I write that. Voila, this mostly works. It looks like we're failing mixed case and punctuation. It looks like specifically the input has an uppercase F, uppercase Z. We're not converting that to lowercase, so that's failing. What we need to do is actually convert the string to lowercase. We could do that inside of the loop, but that's not very efficient. We could do that before the loop. I could say input equals strings dot to lower input. Let's see if that solves the exercise. Voila, we passed all the tests. Yeah, that's how I solve pangram. If there's no questions on the stream, I will move on to the next exercise I have queued up. It's 5 minutes. I have an hour to fill. I hope I'm not going too fast here. So once again, I'm taking the input string, I'm converting it to lowercase, which handles uppercase letters in the string. I'm going to then iterate through the alphabet A through Z one at a time. If the letter A through Z is not in the string, then it is not a pangram. Otherwise, I get to the end of the alphabet, all the letters were found, then I return true that we did find a pangram. Next up, I'm going to take a look at the parallel letter frequency exercise. Parallel letter frequency. I'm going to launch my computer program, which runs tests every time I save. All right, so this is the skeleton. There's a lot going on in the skeleton already. The stuff that they hand us is pretty full. We see there's a frequency map that maps runes to a count. They give us a function already that counts how many times each letter shows up in the string. And then there's the concurrent part that we need to solve. So what we're actually doing here is the frequency takes a string and it tells us how many times each letter shows up in the string. So if you have a string like AAA, BB, it will say that A shows up 3 times and B shows up twice. That's the frequency map. It's pretty straightforward. It just loops through the string and counts each character. Nothing too complicated. Except we're given here a list of strings, multiple strings, and we need to count how many times the letters show up in each, the combined frequency. For instance, this might be, if we're given a book and we want to count how many times each letter shows up in a book to do statistical analysis. This is used for like code breaking, if there's some sort of cipher that we need to break. And one way to do it is, well, E is the most common letter in English. So you can find the most common character in the cipher, and that is probably going to be mapped to an E somehow. This is used for like a simple rotation cipher, for instance. Yeah, so if we have the string and we want to find the frequency, we could go through the string. We could go through the strings one string at a time and count each one. However, that's not necessarily the most efficient way to do that. Go is really, really good at concurrency. It lets you run multiple threads concurrently, which is different than parallel. They're not necessarily running at the same time because your CPU can only have one instruction at a time, but concurrent means that we might be running one, and then if it gets blocked, we'll run another one. I won't get too much bogged down by concurrency versus parallelism, but concurrency is amazing, and Go makes it really, really, really simple to do. It's where Go really shines. So what we want to do is we want to take a whole list of strings. It could be like, chapters from a book where each page in the book could be a separate string. And then we want to compute the frequency on each page concurrently. And then we're going to add them all back up at the end. This could be used for like, if you're doing image recognition, if you're trying to find, flowers in a photo, you can take the photo and split it up into 1,000 chunks, and then try to search each chunk for this. This is also useful if you want to like download data. if you want to like do a search result and get the result, you could send off like 5 search queries in concurrently and then see which one comes back first. So there's a lot of really cool stuff you could go to with concurrency. I guess more practical applications like a web server, if people are making different requests, you could be looking up different pieces of data for them, and then you don't necessarily block each other. Enough about the concurrency and more about the coding. So what we need to do here is we need to take our list of strings, and we need to figure out the frequency of each string, the frequency map, and then join them back up. So in theoretically, each string, we could check the frequency of it by itself. And then, however, in order to tally up the final frequency, we need to combine these all together. So the way that we're going to do that, we're going to have a total frequency map that we're going to use to combine all the parts. And we'll get to figuring out those parts in a moment. So for each part, for each card in part, update total, and we're going to return the total at the end. We want to calculate frequency map for each string. All right, so for each string, we need to calculate the frequency map, then we're going to combine these into a total map at the end. The way we could combine the way we could generate the frequency map for each part is we could do something like for cat index input in range L, I don't know why these L for a variable name. We could call the frequency S, input. So this will call the frequency function with each input piece, each string. The trick here is that we want to run this in parallel. And the way you do that is with the go keyword. And the go keyword takes a function that it calls. So we need to define a function that takes no arguments and calls that, and we want to run that. So this is sort of the, this is the syntax to run the function concurrently. So the go keyword runs it concurrently and just sort of spits off a thread that executes by itself. So this will call the frequency map with each input, and each of these will generate a frequency map that we need to somehow store. So we could build a, there's different ways to do this. We could build a list of values, but the way that we usually deal with concurrency is with channels. A channel is a pipe that one person writes to and someone else could read from. So we could have the go routine write data into this channel, and then we could read data out of the channel, and this could happen at the same time. So like this does asynchronous blocking and all that, which I could get to a bit more in a moment. But in order to do that, we need to create a channel. We can use the make keyword. We want to make a channel, and the type of the channel is a frequency map. So this creates a channel that could hold a frequency map object. We could write a frequency map into and pull a frequency map out of. You could think of it sort of as a queue, like a work queue. And then what we're going to do is every time we call the frequency in this go function, we want to write the results. When we get the results, we're going to write it into the channel. And then the frequency for each part might be very quick, it might be very slow. We don't know. So these various pieces of input, they might take moments to run, they might take minutes to run. But as soon as they finish running, however long that takes, it'll get put into the channel. And then what we could do is, while this is running in the background, we could actually pull that data out of the channel. So part one might be done right away, so we could pop that data out of the channel, and part two might be still chugging away in the background. But that's okay, because we can work on it one piece at a time. So what we're going to do is we're going to pull pieces out of that channel. I'm going to iterate over the input again. I don't actually need the variables, but if I put in if I expect my input has 10 strings, then I expect to pull 10 strings out of that map. So I can use just a for range to make sure I'm pulling out the correct number. For each part, I'm going to pop out a part from the channel. We could do something like our part frequency map, and then pop it out. And then what I'm going to do is for each frequency map that I pop out of the channel, I need to add it to the total frequency. So I'm going to do for character count in my map that I popped out. Then I'm going to update the total with that. Total frequency char plus equals count. So again, what I'm doing here is I'm going to put the 10 inputs. I need to pop out 10 outputs from this channel. This line pops the output from the channel, and then the output is just a frequency map. So I'm going to iterate over the frequency map that's computed for that specific input. Forgot you were going live. Sorry there wasn't any notifications. Unfortunately, we don't have notifications in Discord about going live. We should totally fix that, though. But this will be uploaded later, and you could catch it later. But yeah, so sorry about that. Getting back to the exercise, the concurrency, once again, from the top here, I am, for each input piece, I'm going to send this input piece into a routine that will calculate the frequency for that piece and shove the results into a channel. And then if there's 10 inputs, I need to pop 10 outputs out of that channel. For each one, I'm going to iterate over that map and add it to the total. And then when we get to the end, that should give me the total frequency. Then I'm actually going to combine these lines into one by just ranging over the channel directly, and then I don't need a temporary variable. The one caveat with this is that we have a problem with, I forget what they call it in Go, but the problem is that the loop over here, we're going to, every time we iterate, it updates the value of the input variable. And that input variable is what we're passing to the frequency function. So we're going to take, if the input is, for example, the strings A, B, C, D, every time we start the loop again, we're going to update the input from A to B to C to D. And the function is going to have a copy of that same string, which means we're going to kick off 4 instances of this frequency function in the background. But the input is the same shared input. So all these functions will have, first one will have the string A, and then we're going to update that string to B and kick off a second function. Now both functions have B, and then we'll have 3 functions that will all have C. So what we need to do to prevent this issue is to sort of shadow the input. We need to create a local version of the input that isn't updated by the loop. This is shadowing. What it does is it makes a more localized version of the input. It looks like it's not doing anything, but it actually changes the scope of the variable. So we're making a more finely defined scope for this variable, which the frequency function could get a handle on. But when the loop iterates again, it doesn't update that value. That's one of the really tricky parts about trying to do this sort of stuff in a loop. With this, something very similar in Python, where you late bind functions, you declare partial functions inside a loop, and then you have the same loop variable that's changing under you. But let's see if this actually runs. I wrote a bunch of code, I didn't run anything. Syntax, missing channel element type. I'm misdefining my channel. Let's see if this is how that works. Unexpected, no. How do we define a channel? I don't even know. Go channel definition. I'm going to quickly search for this. C : equals make chan int. I thought I got that. Oh, I'm missing the make part. Am I doing it wrong? Okay, I'm not sure what I changed, but it's happier. This is complaining about the syntax. I may have that wrong. I don't know if you got it this way. You write the data into a channel. This up here should be the channel variable. New variables on left side of : equals line 26. right. Just do for range L. And voila, this actually passes all the tests. I don't know how to pronounce that name. In the Twitch channel, someone says another option is to make the anonymous function take an argument, which also makes a copy. Totally. So rather than doing the shadowing this way, we could essentially do the same thing by doing a shadow. We could say, v, let's call it copy string, and then we could call the thing here with the copy, and then we could do input. So this is another way of essentially creating a localized copy of the string by defining a function. The anonymous function here is saying this function takes a parameter copy, and then we call it with the input, and then that will create a copy for us. So if we run this, it also passes the tests. But if you want to see this not work, let's actually have the issue. It would be more interesting to run this first with the issue. So over here, what I'm doing is I am not creating a copy of the input, and that generates the wrong results. Unfortunately, the test doesn't give us too much detail, so it's hard to know what exactly went wrong. But what's going wrong is, as I explained earlier, the input changes inside the function. The string is getting updated, so we're getting the wrong results. So either way, you could fix that with the by adding that as an argument to the function, or by doing the shadowing here. I find this is slightly cleaner because there's less variables to track, and like the variable name doesn't change on you, but both are equally good. Yeah. So that goes parallel letter frequency solved using concurrency. And again, the really cool thing is, as I mentioned earlier, this function could be running with like one instance could complete instantly and the other one could be running for minutes. But we could actually process them as they're running. So if you have 10 inputs and 9 of them complete very fast, or like, maybe none of them run relatively quick and one is a little bit longer. So the last one could be holding us up, but we don't have to wait for the other 9 pieces for the 10th one. We could actually finish tallying up the first 9 while the 10th is running. And the way that the channels work is this is a blocking operator. So if the 10th piece is not yet ready, this will wait until it becomes ready. Reading data from a channel will block until data is put into the channel. You do need to do a little bit, there's various things about like closing channels and making sure the channel's still open. A really easy way around that here is that we're using the input. We know how many pieces are getting written into the channel, so we could read exactly that many pieces out of the channel. It's a really easy way to sidestep the whole problem of knowing like how many times can I read from the channel? Do we have to close the channel somewhere? All that we don't worry about, just because we know how many pieces are going into the channel, so we read that number out, and it just makes things easier. All right, so that wraps up the concurrent frequency exercise. I am not going to hit an hour on this, but I hope that's okay. And then the third exercise that I was planning on presenting here is the binary search exercise. So I will open that up. I will change directories here, binary search. I will restart my tests. Cool. So this is a new exercise. This is the binary search exercise. What this exercise asks is that given a sorted list of integers, we want to find if a specific value is in the list and what its index is. So if our list is, 1, 2, 5, 6, 8, 11, and the key is 5, we want to figure out that the key 5 is at position index 0, 1, 2. So search inst should return 2 because that's the index of the value. This is really easy, generally speaking, to solve. Like you could just walk through the thing one element at a time. We could iterate. I guess I could implement that first. We could just say for I is 0, I is less than length list, work in Go. I++, what am I doing? This is terrible. For index value in the range list, if value equals key, return index. There we go. And then per the specs, if we don't find it, we want to return -1. This should pass the test in theory. Cool. Great. Very easy solution. Unfortunately, this is an order n solution. If the list has 100 elements, we might need to literally walk 100 values till we find it. If any of you have played Guess the Number, where someone guesses a number from 0 to 100 and you got to guess it, you could say, hey, is it 1? No, higher, 2, higher, 3, higher, and you could just walk your way. It'd take you forever to find it. But you could solve this much more efficiently by using a binary search, where what we do is, since it's sorted, we could say, hey, is it in the middle? And if it's higher, then the search space is halved. If it's lower, the search space is halved. So rather than guessing, like if someone says, guess a number from 1 to 100, you can say 50. If it's higher, then you go 75. If it's higher, you go 87. And this way we split the problem in half with every guess. And this is a logarithmic, a log-based 2 search, and then I believe it takes about 7 guesses roughly to guess the number from 1 to 100. Maybe that's 8. But yeah, if the number is from 0 to 0, then you need 1 guess. If it's from 0 to 1, you need 2 guesses, or I guess 0 to 2, because you guess halfway down the middle 1, and then you get higher or lower, and then you guess it. If it's 0 to 5, we need 3 guesses, something like that. Just some sort of logarithmic growth, where roughly doubles and adds 1. Where you can say sort of 4, 8, etc. So by splitting the problem in half repeatedly, we get, instead of having a order n solution where it takes up to 100 guesses to figure out if the numbers in the list from 0 to 100, we get it in about 8 guesses or 7 guesses by splitting the problem in half repeatedly. So how do we go about doing that? So as I sort of demonstrated, we want to guess halfway down the middle. We want to say, hey, the number is somewhere between 1 and 100. Try in the middle. If it's higher, we go from 50 to 100. If it's lower, we go from 0 to 50. Our search space isn't exactly the number 0 to 100, but it's in this list. However, we are promised that this list will be sorted. So we could guess the middle element in the list, and then we could go higher or lower from there. So what we're going to do is we're going to maintain a ranges. We're going to say it's somewhere between here and here. We can start from 0. We're going to maintain a low and a high guess. And these are going to be indexes somewhere in the list. And those are going to start off as 0 on the low side, list on the high side. It's probably bad form to pack it like that. So we're going to guess that the number is somewhere between 0 and the length of the list. That's probably off by 1 because it can't be the n+1th element. All right, so what we're going to do is we're going to continuously guess in the middle until we guess it. Thank you. Length list. There we go. What we're going to do is we're going to try to move the high and low towards each other until we guess it. And the way we're going to, while the low is less than the high, it should be 4. I read a lot of Python. I don't read a lot of Go. We're going to try to find the midpoint between high and low and say, is it above the midpoint or below the midpoint? The midpoint would be low plus high over 2, the average value. Since these are integer divisions, this will be rounding down instead of rounding up. We're taking the exact midpoint, which is somewhat relevant. And so we're taking this midpoint as our guess. Here's halfway down the middle. Is this the number? So the value would be the list at mid. And then we care about, we're going to compare this value to the key. Are we too high, too low? If the value is equal to the key, for instance, that means we guess the number and we know the index. The index is that midpoint. We just return mid. Conversely, also if the value that we're guessing is less than the key, it means the key is higher, so we need to go higher. So this is sort of like if we guess the middle and we need to go higher, we need to increase our low point to the midpoint, which I hope makes sense. So that means that the low, we had it like in the case of 0 to 100, if our low was 0 and our high was 100 and we guess 50 in the middle, and if the value is too low and the key is higher, then we need to move our low from 50 to 100. So we're going to increase the low to the midpoint. I'm going to throw in a +1 here because we know that the low isn't at the midpoint. It's actually, if it's higher than 50, we can start at 51. We're one value up. I'm actually going to change these around. Key is bigger than the value. I think this is slightly easier to read. So the target that we're trying to guess is the key. So if what we're trying to guess is larger than what we guess, we got to go up. And then conversely, on the other side, also if the key is less than the value that we guessed, we need to move down. So we're going to take the high end and reduce it. I'm not going to throw in a -1 here. Probably could. I think this might break, but we'll give that a go. So yeah, this should continuously change our this will continuously change our low and high and have our search space every time we loop until we eventually guess the right number. And if we get to the end, since we have this for loop that checks if the low is, I guess I should explain how I got that. But when we get to the end, we return -1 if we don't find it. So what's it mean to get to the end? So like, let's assume that our high and low, let's say we're guessing from 0 to 5. So the midpoint, so if we're guessing in the range of 0 to 5, then our midpoint is going to be the average. It's going to be 5 over 2 is 2.5 rounded down is 2. Let's assume it's below 2. So then we're going to be guessing from 0 to 1. Then these are indexes and not values. So like, let's assume that the actual values are like, 5, 10, 20. So we're going to pick a midpoint of 0. And then if the value is lower, then we're going to have 0. We're going to update the high downwards to the midpoint -1. And at this point, the high is less than the low. So this is how we sort of get to the end of the loop and break out, because the high is no longer greater than the low point. I don't know if I explained that well. This gives us an error. I'm pretty sure it's that. Oh, great, I've got a bug. I get to figure this out now. Okay, so the error that we're getting is the list is just the, we have a list of 1. Yes, the list has a length of 1 element in it, and we're searching for that element. So that sets our low to 0, and our high is the length of list, which is 1 minus 1, so the high will be 0. So we're searching between 0 and 0, which unfortunately will fail right away because the low is not less than the high. So this will exit immediately until we don't find it. So we actually need to allow that the low and the high could be the same value. Now if we run this, it passes. I should have cut that over here, but yeah, so we actually need to run this until the, if they're the same, we continue to search, because if the list is of length 1, we do need to still check if we found it. If we didn't find it, then the low would move up or the high will move down. They'll cross each other, and then the low will be greater than the high, and that's an indication that we did not find the result, and we return -1. So once again, I'm going to go over this really quickly. What we're doing is we're given a list of inputs that are sorted, and then we need to take this list and check, split in half repeatedly until we find the value. So as long as we have balanced it properly, this will run until the low and the high cross each other, whereas think first points out you could actually get them until they're equal by tweaking the off by ones a bit. So we're going to take this high and low, we're going to split it down the middle, we're going to check if the value is found, we're going to return we found the value, otherwise we update the boundaries, splitting the list in half until we eventually find it. Yeah, that's how I solve the binary search problem. I could stop here, but I could solve single linked lists. I guess I have the time. I may as well push on through and move on to single linked lists. Simple linked lists. Let's see if I can pull this one off. Simple linked list. All right, next exercise, simple linked lists. So traditionally, if we have a list of values, these are usually stored in an array. We create an array, we could add values to it, we could remove values from it. That's great for some applications. For other applications, we don't necessarily want to have to grow the list every time we add an element. So another way of approaching this is by using a series of linked elements. The linked list could just be defined as a pointer to an element, and each element, if there's another element following it, they will point to each other, which gives us a bunch of linked elements. And that's what we're being asked to implement here. So the element that we need to define here is basically the node in the list. This linked list is also like, if we change it slightly, this is also how you get trees and graphs and binary trees. You basically have a bunch of nodes that could have, like in a tree, typically in a binary tree, each node has two children, a right and a left. This allows us to build binary trees and sorted trees and a whole bunch of other types of trees. You could get fancy into like K trees where you have like 3 or 4 children. This could be used to build a graph where, for instance, if we wanted to do like a traveling salesman problem where you have a bunch of cities that are connected, and you might say, to get from city A to city B is this much travel distance. So you could have a link from A to B, A to C, A to D. And these are all sort of nodes that have pointers to other nodes. But the type element is our node. And we're going to implement it using a struct. Each node in this particular problem yes. Akel, if I'm pronouncing that correctly, pointed out that the new function doesn't actually have a name here. That probably is a bug in the stub that, yeah, we should probably fix that in the stub. That's a great thing to open up on the forum and see if the maintainers are interested in a PR for this. You could definitely push a PR to our GitHub repository to fix that. It should be like values or something. Yeah. All right, so we're creating a node for a linked list. Each node needs to have a pointer to the next element. So we'll have a next element pointer. And then also some of the data that we want to store in each node is a value. In our case, those are going to be integers. Yeah, and then by stringing a bunch of elements together, we could create a linked list. The type list, I'm also going to use a struct here, and then the linked list could be defined by just a pointer to the root or the, so since it's actually like the tail, the last element in the list, because we're doing a FIFO last in first out of stack. So there's 2 ways to organize this linked list. We could either maintain a pointer to the first element or a pointer to the last element. Then as we add elements, depending on which way we order it, we either have a queue where the first one that comes in is the first one that comes out, or we could have a stack where the last one that goes on is the first one out. Either way it works, you could think of it as like a stack is like when you stack documents on a table, where if you stack books, the last book that goes onto the stack is the first one you take out, compared to a queue. If people are waiting in line in a queue, the first person who goes into the queue is the first one who comes out. Those are 2 equally valid ways of defining linked lists, but for the purposes of this exercise, they expect you to use a stack. It's explicitly a LIFO, last in first out object. So I'm going to define my list just by saying that my list, I'm just going to maintain a pointer to my last element, and then, which I guess would make this a previous. So I'm going to maintain a pointer to the last element. If I push in a new element, I'm going to track I'm always going to track the most recent element that got pushed, and each element could point to the prior element. So let's actually get to implementing some of this stuff. To create a new list, I just say, list is a list object. I'm going to initialize an empty list object. And then if I'm given a list of values, I need to push those values into the list one at a time. Fortunately, I'm later going to implement a push function, but for now I could just say list.push element to push elements into this. And then given a list of values, I could say for element in range of values, push the element. And this should return a list with all those elements pushed. Unfortunately, in order for that new function to work, the push needs to be defined. I'm just going to return there so it doesn't die. And then let's see if I could actually run this. Missing return. Yes. This function doesn't return the list. We should fix that. Return list. Can I use list? Yes, this is complaining that I created a list object and not a pointer, and it expects a pointer back. So we change that as such. Sweet. Something's changed. It's complaining that my size function is not implemented. So my new function may or may not be working. But let's assume for the moment that it does work, and then we could implement the size function. Maybe I'll actually start with the push function, because this is sort of essential to make our lists. All right, so in order to push an element to our list, what we're doing is we're maintaining a pointer to the most recently pushed element. So if you imagine like a stack of books, we put on a new book into the stack, and we need to maintain a pointer to the top book. And that's going to be our last element. So we're going to create a new element. When we push an element, we're going to say element is a element object, and then this takes the value, which is the element, and then it takes the previous one. So when we have a stack of books, we're currently pointing to the top book in the stack, and then when we put another book on top of it, the old top becomes the previous of the new element. So if we take the l.last, this is the old top book, and then it becomes the previous from the new element. And then this puts the new element on the list, and then the new top element in the list becomes that element. And we could actually combine these two statements into one, simply by saying l.last is the new element. And then the new element will maintain a pointer to the prior element all the way down. So this will give us each new element points to the previous element, which points to the previous element, which points to the previous element. And if there is no previous element, when we first create the list, if we have an empty list, we initialize last as an empty element as nil. So the first time we do this, that will just be a nil pointer. So let me write this code, see if there's any syntax errors. There are not. Cool, that seems to have worked. I was able to write one line of code without a syntax error. Go me. Cool. So in order to determine the size of this list, one of the downsides of using this is that linked lists are sort of expensive because you got to walk the entire list. We could walk the entire list to figure out the size. Another shortcut some people like to use is they'll actually maintain the size as a separate piece of data in the structure. So we could update our list to have a size int, which is a much more efficient way of doing this, but I'm going to do this the hard way and actually walk the list to figure out the size. So in order to walk the list, what we need to do is we need to maintain a pointer to an element and just move from one element to the previous, to the previous, to the previous until we get to the end. So I'm going to initialize my size to 0, and my current is going to initialize to the list.last. And then this says that initially we have a zero size list, and then we're just going to increment the current from the current element to the prior to the prior to the prior until we run out of elements. So in order to do that, I'm actually going to use a for loop. So the current starts pointing to the last, and then as long as the current dot previous is not nil, there's another previous element, I could update the current equals current dot previous. And then inside the loop body, I'll just say size plus plus to compute the size. And I could just return the size when I get to the end. So again, what I'm doing here is I'm starting off with the zero size, and then I'm going to use the current to walk the list. Instead of walking from 0 to n, I'm going to use a for loop to walk from the first element in my list until the last element. So as long as there is another prior element in my list, I'm going to increment the pointer and increase the size by 1. Let's see if this works. Invalid memory address or nil pointer to reference. I am doing something wrong. If I have an empty list, I'm going to start my current is pointing to the last, which might be nil already. So current might be nil from the very beginning. And then if I do current.previous, I'm going to run into an invalid null pointer. So I can't actually test that. I think I have an off by 1 here. So I think what I need to actually do, say while current is not nil, then I could increment it. And looking at the tests, it's not complaining about the size function anymore, so hopefully it's working, which means we can move on to the pop function. The pop is just the inverse of the push. When we push, we take the last element on the list, and we assign it to the new element that could put on top. What we've got to do now is the inverse. We want to take the top element off and tell the list to point to the next element. So what we're going to do here is first we need to grab that value. Value is all.last.value, and then we're going to return that value. And this returns the value we need, and then we're going to set the error to nil. And then we need to update the list to remove the top element. The way we do that is by saying l.last is l.last.previous. And this will just walk the list one step and will maintain the prior element as the new top. And that more or less should be all we really need for this function. Well, it hasn't complained yet. We will get back to this when we pass other tests and it starts complaining about stuff. Next up is the array function. What this asks us to do is to return a list of integers corresponding to the values in the list. The way we're going to do that is, again, we're going to walk the list one element at a time and put those values from the linked list into a regular array. So we need to, first we're going to get the size so that we could make an array, an int array of size. And then we could put elements into this list one at a time. We could use the append function. I'm going to actually just pre-create the array. And I'm going to iterate over it and assign values. We're going to do that. I'm going to steal code from my size list. We're going to walk the linked list one element at a time and shove them into the array. So I'm going to start at the top of the list and move down the list one element at a time. And then for each element in the list, I'm going to say array of I is equal to current.value. What is this I magic? I should define an I variable. I is 0. And then I'm going to do an I++. So every time we run through the loop, very similar to tracking the size, I'm going to maintain an index and just shove the value from that linked node into the array at that position. And then once I get to the end, I could return the array. Invalid memory address. Sample linked list, line 34. Cool. I will ignore that. That isn't the pop function. We'll address that at another time. We will fix all the bugs when I get to the end. Reverse. The reverse is a cute one. What we could do here is, so since we have a LIFO, if we, for example, push values 1, 2, 3, when we pop them, we get back values 3, 2, 1. And then if we, one of the cute characteristics of a stack is that if you pop them and put them into a new list, you get the reverse. If you ever play like the Towers of Hanoi, or if you have like, if you imagine, two piles of books. If we take the top book off one pile and stick it on the other pile and repeat this over and over, we actually reverse the order of the books. So if you have books A, B, C, and then we take C, put on the new pile, take B on the new pile, put on the new pile, and we end up with the books in the reverse order, A, B, C. So the way we could actually reverse a list is simply by moving them from one stack to the other stack in order. So I could create a new list. Reversed list, which will just be a new, and I'm going to call this with nil or an empty list. And then what I'm going to do is I'm going to have to pop values. We don't actually want to pop because that'll modify the values. We don't want to pop values because that modifies the input. We don't want to modify the input. We don't want to do that, but we could walk the list one element at a time. So again, I'm going to steal this for loop that walks through a list. And then for each element in the list, I could just push the current value into the reversed list, and I can return reversed. So again, I'm just going to create a new list, and then I'm going to use this exact same for loop that I've been using over and over that walks through my list, and for each element in that list, I will push it onto the new list, and that will reverse the order and create a new list I can return. And now I'm forced to confront the fact that I've got some bugs in my code that I haven't addressed. The first test we see here on the right that's failing is test pop from empty list. My list is empty, I can't pop values from it. And that shows up because I have a invalid memory address for a nil pointer dereference. Found in panic, there's the test code, I don't care about any of that. Simple linked list, that's my code, line 34. Line 34 is over here. There we go. So what's complaining about over here is that the list.last could be nil, so it doesn't have a value, so I can't access the value, which is why this pop function could potentially return an error. In order to handle that, I'm going to go to the top here. I'm going to import errors, which I failed to import earlier. Scroll back down to my error over here. All right, so what we need to do is check that there's actually values in the list before we start popping values. So I could say if l.last is nil, then I have an empty list and we can't pop values from it. So I could say, if it's nil, return 0, errors.new pop list is empty, exclamation mark. I'd like to start with a lowercase letter, so cannot pop, list is empty. Let's see if that makes the test happy. Sweet. The pop is now happy because I have a error check over there. What else is there to fix here? Let's take a look at the non-empty list to array function. So if we look at the list, this says that it wants test on an empty list array. It gets back 3, 2, 1. It wants 1, 2, 3. So that looks very clearly like I'm populating my list in the wrong order. So if I push values 1, 2, 3 into my linked list, when I walk the list from the top to the bottom, I get 3, 2, 1, and I'm pushing 3, 2, 1 into my array because my array goes from 0 to n, and I'm going to push 3, 2, 1 into the array. which unfortunately is in the wrong order. Various ways to fix this. I'm simply going to change my index. Instead of going from 0 up, I'm going to start it at size -1 and go downwards. So this will populate that inner array from the top to the bottom, which is why I didn't use append, because I saw this coming. I run my tests. Everything passes. It looks like the array function gets used heavily in testing, and if that works properly, everything is happy. Yeah, so that's my passing tests for simple linked lists. If there's any questions on the Twitch stream, I could try to address that. If everyone's happy with the solution, I will sign off in a minute. Thank you very much for joining us. I hope you have fun with Mechanical March and with Exercism in general. Quick plug, please do make use of mentoring. There's a lot of mentors out there who are waiting for people to submit solutions. I've had many, many students who was like, oh, why not? I'll mentor and see what, I don't expect a lot, but I'll give it a go. And I've had a lot of reactions of, oh, I didn't realize I could learn so much from the simple exercise. I thought it's a really simple exercise, but I came away with so many things. So the mentoring is the code reviews, as they're calling them now, is a very valuable experience where you get to interact with a mentor who hopefully has a little bit more experience than you do at this language and could teach you a whole bunch of really cool stuff. Yeah, that's all I've got for you tonight. So with that, I will sign off. This is Isaac Good with Exercism. Have a wonderful month or year with Mechanical March and with the 12 and 23.